Okay, students, I want us to begin the lesson, and they have started to record now. So I want to introduce you to the quantum theory of the atom. We have already discussed the theoretical development of the atom, and today I will be taking you through the quantum theory of the atom. And the contents of today's lesson, just a moment, please, just a moment, I'll be back. Just a moment. Just be back. Sorry for that. So for the content, are you able to hear me?
Yes. Yes.
Thank you. Sorry for that. So for the content and the concepts, I will be taking you through the quantum mechanics and the quantum numbers. We will borrow from the theoretical or historical development of the structure of an atom. Remember, we started with the Rutherfords, J.J. Thomson. We talked about the Bohr theory. Now, all those theories are building up slowly so that we can get somewhere. When we talked about the J.J. Thomson's theory, we talked about the presence of the protons and the electrons, but we were not sure where these protons are and where these electrons are. When we moved to Rutherford, he was able to tell us that we have the positive nucleus where we have the protons. Now, around the nucleus, we do have electrons, but he was not able to tell us where specifically those particular electrons are found. When we go to the Bohr theory, we discussed last time the Bohr theory. Bohr theory is able to tell us, yes, in the nucleus, we do have the protons. And then these electrons are going to be found in specific regions that we called the energy levels, the orbits. Now, in this particular lesson, we are going to build up from that Bohr theory so that we can say, if an electron is in the first orbit, if an electron is in the first energy level, where exactly are we likely to find that particular electron? And now this is what we'll be discussing today in quantum mechanics and quantum numbers. And that is why we are saying that the Bohr theory firmly establishes the concepts of energy levels, but it does not account for the details of their atomic structure. It does not tell us within that particular orbit, where are we likely to find an electron? What is the highest probability that an electron is going to be found within a particular region of space? If I am too fast, again, I would request you to remind me so that I can go at a pace that is suitable for all of us. Are we together?
Yes.
Very good. So we go on. Let me pull down something here so that I can have access to my notes. So we are saying that here we are discussing some both basic notions of quantum mechanics, which is the theory currently applied to extremely small particles, such as the electrons in atoms. And therefore, we'll be looking at quantum mechanics and quantum numbers, as well as orbitals. And what are the learning objectives of today's lesson? Under quantum mechanics and quantum numbers, we will be talking about the de Broglie statement. Remember last time when I was teaching you, I said that matter can behave as a particle. It can also behave as a photon of light. This is what we call the dual nature of matter. And I mentioned briefly that that is discussed by de Broglie. And therefore, we are going to say a few things about the de Broglie statements. Then we are also going to define the quantum mechanics and then state the Heisenberg uncertainty principle. We will therefore relate the wave function of an electron to the probability of finding that particular electron in a particular region of space, which we are going to call an orbital, and we are going to see as we continue. Then when we talk about quantum numbers and atomic orbitals, we will be able to define what an atomic orbital is. We define each of the quantum numbers, the 4 quantum numbers that I am going to talk about in a short while. And then we state the rules that are going to be allowed for the values that we will assign to each of the 4 quantum numbers. And we will apply the rules for quantum numbers. And when we are applying these rules of quantum numbers, we'll be able to determine how many electrons can maximally be accommodated in the first energy level, how many electrons can be accommodated in the second energy level, how many electrons can be accommodated in the third energy level. Remember, in the last lesson, we were talking about 2 electrons in the first one, 8 electrons in the second one, 18 electrons in the third one. And this is a slight departure from the theory that you know. Previously in the high school, we have taught that there are a maximum of 8 electrons in the third energy level. But we are going to illustrate here that that third energy level can actually accommodate a maximum of 18. And I will be able to explain where these 10 are coming from. We will be able to describe the shapes of the atomic orbitals. And here we will actually talk about the S, P, and the D orbitals. Now, when we start the content, the first question is, why are we saying that an electron can behave as a particle and the same time as a wave? Why do we use an electron and describe it in the concept of the dual nature of matter? And we are saying that the fundamental concept of quantum mechanics is that matter will behave as a wave and also behave as a particle. We have matter having 2 different kinds of properties. It has the properties of a wave. It also has the properties of a particle. And that explanation of that concept was hypothesized by de Broglie, that if light can behave as both as wave and a particle, it therefore means that all matter, and here we want to confine ourselves to electrons, protons, and neutrons, can also behave as waves. And this is what we are showing here, that electrons can behave as waves. They can also behave as particles. And when we look at that, then we can have these equations that I'm showing you here. If you look at this particular equation, we are saying that momentum, P is for momentum. Momentum is equal to the mass of that particular particle multiplied by velocity. This C here is for velocity. When you actually read books, you find that P is equal to m nu for velocity. And remember this velocity here, we were able to give the relationship between a frequency, wavelength, and the speed of light. And that is where we are getting this kind of an equation from. H nu over C. C here is the speed of light, which is 3.0 times 10 to the power 8 meters per second. In the quiz that we gave you, it was 2.998 times 10 to the power 8 meters per second. You only use the value that we give you. So here we are using nu over C. And it can also be given by this. Where does this one come from? C is equal to lambda mu. And I showed you this relationship last time. So that now, if you have lambda here, then that lambda is equal to C all over nu. Let me accept a student who has just joined. And if you look at this one, this is the same as 1 over lambda. So if it is 1 over lambda, it means that we are talking about the reciprocal here. And that is why this one is up and this one is down here. Okay? You can stop me at any point and ask a question so that we do not leave any student behind. Okay, let me do away with this so that the writings, so that very good. So this is these equations are just showing that we can have matter and talk about a photon of light. We can also have matter and talk about a particle, as shown in these particular equations. Okay, now we go to something we call the uncertainty principle, or the Heisenberg uncertainty principle. And here we are saying that, just a moment, I pull down my, just a moment. The Heisenberg uncertainty principle is borrowing from the dual nature of matter. And what does it say? That it is impossible to determine both the momentum and position of a particle simultaneously. In other words, the position and momentum of a particle cannot be determined simultaneously. Mathematically, we can use what we call the probability density, psi squared. This sign you see here is psi, and here we are writing psi squared. We want to think about the probability of finding an electron in a given region of space. And when we look at this in terms of the Heisenberg uncertainty principle, you can see we have this mathematical expression here that we have delta x. This is in terms of the position, and the delta p, change in momentum, is equal to h over 2 pi. And that is the mathematical expression of the Heisenberg uncertainty principle. The building on de Broglie's work in 1926, there was the Schrödinger himself, who came up with a theory which could be used to explain the wave properties of electrons in atoms and the molecules. And the branch of physics that mathematically describes the wave properties of submicroscopic particles is what we call the quantum mechanics or the wave mechanics. These are actually a branch of physics. The wave-like property of the electron, and we say that an electron is viewed as a standing wave. So here we are looking at it as a wave. And for us to be able to describe where we can find that particular electron, we use a mathematical function psi, which we are showing here, psi here. And that is how we pronounce it, psi, which we call a wave function to describe the wave-like behavior of an electron in a given region of space, which we call the atomic orbital. And the drawing that you can see here, the graph that you can see here, is that of a wave function. And you can see that we have drawn two wave functions. Now, one is that of probability, and the other one is of probability density. The red one is for psi, the blue one is for psi squared. And we are interested in the one for psi squared because it is the one that gives us the probability of finding an electron within a given region space. If I just show you, let me see whether I can draw something like this. Now, if you look at what I have here. Now, assuming that the inner one is our nucleus and the outer one is actually our first orbital, n is equal to 1. Now, if we have an electron here, the question would be, how sure are we that this electron is here and it is not in this particular region? It is not in this particular region. Remember, this is a circular path. So what is going to give us the highest probability that an electron is going to be found in a particular region here? And that is described by the probability density function, which is the psi squared. And we say that this function psi squared is the probability of finding an electron in a given volume of space, and that volume of space is what we call an atomic orbital, which I am going to illustrate as we continue. Any questions so far from the students?
Yes.
Yes, ask your question.
Okay, it's not about the Heisenberg uncertainty.
Yes, yes.
It is on the other slide.
Yes, it is here.
Explaining about the quantum mechanics.
I'm not hearing you very well. Please come again. Yes, I can hear you. Lindsay, please continue with your question. Okay, we seem to have lost her. Any other student with a question? Yes, Kadisha.
My question was on the dual nature of matter, whereby we were saying that mc is equals to h nu over c. So my question is, the velocity and nu in this case, we take it as the same thing. I couldn't understand that part.
Very good. Now, what I'm saying here is that this equation here, this one here, is just talking about the c being used here is the speed of light. Okay? This is the speed of light. Generally, the equation is P is equal to mass times velocity of light. Okay? So that is what is used. And that is where we are moving from this to this expression here. Have I clarified?
Yes.
Kadisha. Okay, there was a Lindsay, is it Lindsay?
Yes.
Yes, now ask your question.
Okay, I can't really understand. Would you please remind me how it comes from Planck's constant times the mu over c to Planck's constant over lambda? Kindly.
You want us to move from what?
H
mu
over c.
Yes.
To h over lambda.
Very good. Now, this is what happens. Let me just concentrate on nu over c. So we have h multiplied by nu all over c. Last time I said that c is equal to nu lambda. If you remember that very well. Now, from this equation, we can say that lambda is equal to c all over nu. But now, if you look at what we have here and what we have here, this is the reciprocal of this. Meaning that if we write 1 over lambda is equal to c is equal to nu over c. Is equal to nu over c. And therefore, this one can be written as times 1 all over lambda. And that is how we are getting this.
Okay, thank you. I've understood.
Thank you. So we can move on. Well, so let me continue. So this is the Schrödinger equation, and it shows the relationship between the wave function psi, the energy. Here we are talking about the total energy and the potential energy of the system. And if you look at what is happening here, you realize that this section here is giving the three directions. So it is giving the X dimension, the Y dimension, and the Z dimension. And here we have the energy term of that particular function. So this is the equation or solution gives us the probability of finding an electron within a particular region of space. And that particular region of space is what we call an atomic orbital. And that is why I'm introducing you to atomic orbitals here. And we say that an atomic orbital, which is psi, is defined as a wave function for an electron in a particular atom. That psi is pictured qualitatively as the region of space where there is a high probability of finding electrons at any given time. And using this, then we can say that an atomic orbital is characterized by some quantum numbers. And there are 4 quantum numbers that characterize or that describe an atomic orbital. And the quantum numbers are N, L, ML, and MS. And I'll spend the rest of the lesson today explaining to you each of these quantum numbers and how they apply in the determination of the electronic configuration and the number of electrons that a particular energy level can accommodate. So it describes a region of space with definite shape where there is a high probability of finding an electron within a particular atom. And we will describe or we will study the quantum numbers first, and then after that, we will look at the atomic orbitals. So, according to the quantum mechanics, each electron is described by 4 quantum numbers. So any electron that you find in an atom must be characterized by these 4 quantum numbers. And what are these quantum numbers? We have number 1, the principal quantum number, N. And this is normally what we call the energy level. When we say that the first energy level, N is equal to 1. The second energy level, N is equal to 2. the third energy level, n is equal to 3. So we actually call that one the principal quantum number. I mentioned it last time, and I said that I'll be talking about it at length in today's lesson. Now, when we look at the values of n, they will give you the second quantum number, which is the angular momentum quantum number, L. So for every value of n, we are going to have some values of L. And then for every value of L, we are going to get the third quantum number, which is the magnetic quantum number. And this is ML. What I'm saying here is that the first three quantum numbers are dependent on one another. So that number n, the principal quantum number, is going to generate angular momentum quantum numbers. And the angular momentum quantum numbers will generate the magnetic quantum numbers. So the first three are interdependent in the sense that one must generate the others. The fourth quantum number, which is the spin quantum number, is independent in the sense that it just shows the orientation of that particular electron, whether it is facing upwards, whether it is facing downwards. And that particular orientation is independent of the first three quantum numbers. It is not generated from the first three quantum numbers. And that is why we are saying that the first three quantum numbers are define the wave function for a particular electron that gives the highest probability of finding the electron at various points in space within an atom. And the fourth quantum number is just giving you the magnetic orientation of that particular electron. Having said that, I want us now to go into the details of each of these four quantum numbers. And I want you to listen very keenly because there's very important information which you're actually going to use from now and the rest of your chemistry. Whenever you find it, it is going to rely heavily on this basic information we are giving now about the electrons and how they are arranged in an atom. So the principal quantum number, it is designated by a small n. And we say that this is the one on which the energy of an electron in an atom primarily depends. The smaller the value of n, the lower the energy and the smaller the orbital. And I want to take you back to the Bohr theory. When we were talking about the Bohr theory, we said that an electron can jump from a low energy orbital to a higher energy orbital by absorption. It can also move from a high energy orbital to a low energy orbital by emission. And we also said that these particular orbitals that we have, these particular energy levels that we have, the farther they are from the nucleus, the higher the energy content. It is the same thing that we are saying here, that the smaller the value of n, the lower the energy and the smaller the orbital, meaning that the first energy level, when n is equal to 1, then the energy of that particular orbital is low. When n is equal to 2, the energy is high. When n is equal to 3, the energy is higher, and so on and so forth. These principal quantum numbers can only take positive whole number values, and therefore we have 1, 2, 3, 4. And let me tell you something. When we were calculating the energy involved in electronic transition, remember we did calculations when an electron moves from n is equal to 1 to n is equal to 2, or n is equal to 4 to n is equal to 3. Now, those transitions, I told you that when an electron leaves that particular atom, then n becomes infinity. We are not able to trace that particular electron within any given energy level of the particular atom. So the values that we assign to the principal quantum number are 1, 2, 3, 4. Now, each of these values will actually generate L values, as we are going to see. So orbitals with the same value of n are said to be in the same shell. So I will illustrate this as we continue. Any questions so far? Any question so far from the students?
Okay, so we have the orbitals, we have the orbits, and we have the shells. Okay, orbitals with the same value of n are said to be in the same shell. Shell,
Yes.
can it equate to orbital?
No, a shell is an orbit, is an
Or a shell
energy
is an
level.
orbit? Okay, thank you.
Within the energy level, we are going to have orbitals, the specific regions within an energy level where an electron is most likely found. Clarified?
Yes, sir.
Thank you. So the shells are designated by these numbers. When n is equal to 1, we can use uppercase K. When n is equal to 2, we can use uppercase L. When n is equal to 3, we can use uppercase M. When n is equal to 4, n is equal to 4, we can use uppercase N. These are sometimes used, but in most cases, we use 1, 2, 3, 4. Now, I said that when we talk about the principal quantum number, it is from the principal quantum numbers that we are going to get the angular momentum quantum numbers, the L. And therefore, let me discuss this L. The angular momentum quantum number, it distinguishes the orbitals of a given shell that have different shapes. In fact, this is the quantum number that gives us the shapes of the orbitals, the specific regions of space where the electrons are found, and also their names. So it describes the shapes of the atomic orbitals. And it can have values from 0, 1, 2, 3. What does it therefore mean? The values of L will come from the values of N. And L is going to be from 0 all the way to N minus 1. For example,
Sir,
yes.
there's someone waiting to be let in the meeting.
Oh, sorry. Sorry for that. Let me check. Let me just check now. Thank you for alerting me. Now, who is want to see who's waiting? Yes, there's Lynn. Thank you. You alert me when somebody stays in the waiting room for long. David, you have a question? Okay. So what I'm saying here is that we have n is equal to 1. The values of L will be 0 all the way to n minus 1. What does it therefore mean? When n is equal to 1, L can only be 0. Is that statement understood? Because that is building on the next. When the first energy level can only have one possible angular momentum quantum number, which is 0. When the value of n is equal to 2, then L will be 0 and 1. Because it will go up to n minus 1. And n minus 1 here is what? 1. When n is equal to 3, what are the possible values of L? L will be equal to 0, 1, and 2. This is very important.
So could you explain how when n is 1, L is equals to 0? I'm not understood.
Very good. Look at this statement here. Look at that statement. We are saying that the values of L will be 0, 1, 2, up to a maximum of n minus 1. Okay? So it means that when n is equal to 1, the values of L will be 0 all the way to n minus 1. So the only possible value is 1, which is 0 there. When n is equal to 2, the value of L, they must start from 0. In all cases, they must start from 0. 0, 1, 2, 3, and the last one will be equivalent to n minus 1. So when n is equal to 1, the first one is 0. We go on. What is n minus 1? 1 minus 1 is 0. So it is only this one. When n is equal to 2, the possible values of L are 0 and 1. When n is equal to 3, the possible values are 0, 1, 2. When n is equal to 4, the possible values are 0, 1, 2, 3. It will always go to one value lower than the value of n. Is it understood to the student who asked the question and generally the class?
Yes, so when we get the value of n, we have to subtract by 1 in order to get the value of L.
So that you can get the maximum value of L. All right?
Yes.
They will run from 0 all the way to n minus 1. The last value of L will be n minus 1. Any other question? Okay. So we move on. So these values of L are designated by these letters that we have here. These letters that we have here. When L is equal to 0, we call it an s orbital. When L is equal to 1, we call it a p orbital. When L is equal to 2, we call it a d orbital. When L is equal to 3, we call it an f orbital. When L is equal to 4, we call it a g orbital, and so on and so forth. In this particular unit, we will actually deal with S, P, D, and F, especially when we are filling in
Excuse me,
electrons.
teacher.
Yes.
Excuse me, sir. Sorry for disturbing, but like I don't understand what's L.
You don't understand what L is?
Yes, I don't understand what L is.
Okay. This is how we got L, the angular momentum quantum number. This L here is derived from the principal quantum number. And I say that for every value of n, we will have L values. And these L values are going to run from 0 all the way to n minus 1. Did you understand that?
Yes.
You understood that? Eh? So that is how we are generating
Yes,
the
I did.
That is how we are generating the values of L. Now, those values of L, if the value of L is 0, then we use the symbol S so that we can say that is an S orbital. When the value of L is 1, we designate it by a small p, and therefore we call it a p orbital. When the value of L is 2, we designate it by a small d, and we call it a d orbital. And when it is 3, we designate it by a small f, and we call it an f orbital. And that is what we are showing here. Is it clearer now?
Yes, it is.
Yes, these L values are coming from the values of n. Remember, I said that the first 3 quantum numbers are interdependent in the sense that the value of n is going to generate values of L, and the values of L will generate the values of ML, the first 3 quantum numbers. So then if that is understood, let me explain the magnetic quantum number, which is ML. Now we have talked about N. From N we have gone to L, and we saw that N generated L. Now L is going to generate ML. It is going to generate the magnetic quantum numbers. So this quantum number distinguishes the orbitals of a given N and the L. That is of a given energy and the shape, but may have different orientations. It actually describes what we call the directionality of an atomic orbital. And how are we going to get the values of ML? The values of ML are going to come from the values of L. And how does that happen? The values of ML will be equal to ML will be equal to negative L through 0 all the way to positive L. This is the L which is going to generate ML. What do we mean here? If L, for example, if L is equal to 1, then ML values is equal to negative 1 through 0, then positive 1. If L is equal to 2, are you able to see where I'm writing?
Yes.
If L is equal to 2, then ML values will be equal to negative 2, negative 1, 0, 1, and 2. When L is equal to 3, you realize that the ML values are negative 3, negative 2, negative 1, 0, 1, 2, 3. That is how we generate the ML values from the L values. Is it understood? Any question? Let me see whether there's anybody who has raised their hand. So when you have different values of L, you can get ML values. Yes, yes.
What do you mean the directionality of an atomic orbital? Is it the way it is positioned?
Where it is facing, I will illustrate. Where it is
Okay.
facing, I will illustrate.
Okay, thank you.
Yes, another question? Good. So what can you see? when L is equal to 0, because I've shown when L is equal to 1, we have -1, 0, and 1. When L is equal to 2, we have -2, -1, 0, 1, 2. When L is equal to 3, we have -3, -2, -1, 0, 1, 2, 3. What about when L is equal to 0? The only value of ML is 0. The only ML value there is going to be 0. Now, if you again examine this, you realize that when L is equal to 1, we will have 3 ML values. When L is equal to 2, we will have 5 ML values. When L is equal to 3, we will have 7 ML values. What does it therefore mean? It means that, is there any question? Just want to be sure. Or somebody in the waiting room? No. It means that if you look at the relationship between L and ML, it means that I've gone somewhere. It means that this equation here applies. When you take 2L plus 1, you get the number of values of ML. And those are actually what we call the number of degenerate orbitals. And we will explain that as we go on. So in summary, what we have said about those 3 atomic orbitals, we are saying this, that when n is equal to 1, the number of L values will be 0. When L is equal to 0, the only ML value is 0. We have shown that. Now, when it is 0, we actually call it an s orbital. We call it an s orbital. When L is equal to 0, we call it an s orbital. And therefore, when n is equal to 1, n is equal to 1, L will be equal to 0. And we call this one s orbital. ML is equal to 0. And this tells us how many s orbitals we have in a particular shell. So it means that this shell has only one orbital, and that orbital is what? The s orbital. If you look at when n is equal to 2, when n is equal to 2, you will have 2 values of L, which are 0, and 1. This 0 is an s orbital, and this is a p orbital. Okay? When we look at this as a value of L, you realize that it is going to have only one ML value, which is 0 here. And therefore, this s orbital is found in n is equal to 2. An s orbital in n is equal to 2, we call it 2s. This one is the principal quantum number, which is this one. And this one is coming from the value of L, because the value of L gives us that particular orbital. And you can see that it is only 1. Now, when the value of L is equal to 1, then the ML values are -1, 0, and a +1. Now, this is a p orbital, and it is a p orbital found in n is equal to we call it 2p. That 2p has 3 values. These 3 values are degenerate orbitals, orbitals of the same energy. I will actually use this to show you that directionality I was talking about when we talk about a p orbital. Any questions so far? Okay. So I move again slowly. When n is equal to 3, the values of L are 0, 1, 2. Now, this one is a 3s. Let me write it well. This one is a 3s. Let me admit some students. This one is a 3p. And this one is 3d. May somebody ask me where I'm getting these things from? Do you understand why I'm writing 3s, 3p, 3d? The 3 is coming from the principal quantum number. This 3 is this one here. This 3 is this principal quantum number here. And this 3 is this principal quantum number here. The s here is coming from the value of L equal to 0. When L is equal to 0, that is an s orbital. When L is equal to 1, that is a p orbital. And when L is equal to 2, that is a d orbital. That's why I'm writing 3s, 3p, and 3d in that particular order. Any questions? You'll excuse me for the background noise because I'm teaching from home. If there's no question, then we can continue. When we talk about this, when we talk about this 3p, it will have 3 ml values, and those ml values are what we say the -1, 0, and 1. This one is going to have 5 values, which are -2, -1, 0, 1, and 2. And that is what we have explained here. That is what we have explained here. So when we talk about a 3D, we are going to have 5 degenerate orbitals. And these are the d orbitals, and I will be explaining. In fact, it is these d orbitals that make the third energy level have 18 electrons. The extra 10 electrons are coming from the 3D, and I will be explaining as we continue. So we can use the same concept to illustrate n is equal to 4 and n is equal to 5, whereby we are going to have the f and the g orbitals respectively. Now, when we talk about an f orbital, you know, this f is where L is equal to f is where L is equal to 3. And when you get the ml values, you're going to have -3, -2, -1, 0, 1, 2, 3. And that is where you are getting the 7 orbitals from that I have mentioned here. I can see some students in the waiting room. Let me admit them. So that's why we are saying that in an F subshell, there are 7 orbitals. in a G shell, there are 9 orbitals. Remember, 2L plus 1. So all that information is given in this table here, is given in that particular table here. And this particular table, we are saying, when N is equal to 1, L is equal to 0, ML is equal to 0, we call it 1s orbital, and it is only 1. Now, okay, previous slide, somebody is asking something about the previous slide. Yes, ask a question. Ask a question, specific question about this slide. There's a student who has a question about this slide. Can you ask a specific question? Lynn, are you able to talk?
Excuse me.
Yes.
My network disconnected, so I didn't hear the previous slide.
It is the slide I've just displayed now, isn't it?
Yeah.
Yes. This slide is a continuation of this particular slide here. If you can generate L values from any N value, and then use the L values to generate ML values, that is what we are talking about. In this particular slide, I only showed N is equal to 1, N is equal to 2, N is equal to 3. And for each of those values of principal quantum number, we were able to generate L values and the respective ML values. In this particular slide here, I'm saying that you can use the same approach to generate same values for N is equal to 4 and N is equal to 5. Whereby for N is equal to 4, you're going to get 7 subshells. I mean, and N is equal to 5, you're going to get 9 subshells using 2L plus 1. That's what I was explaining. So this is a summary of what I have just explained. And I'm saying that the first one is here. That is when N is equal to 1. The possible value of L is 0. The possible value of ML is 0. We call it a 1s orbital, and it is only 1. When N is equal to 2, we have these two possibilities. When N is equal to 2, we can get L value equal to 0. When the L value is equal to 0, the ML value is going to be equal to 0. And that is a 2s orbital. Okay? It is a 2s orbital because the principal quantum number is 2 and the L value is 0. The S is coming from the L value. The 2 is coming from the principal quantum number. Now, again, when N is equal to 2, there's another value of L that we can get. This is the value. And this value of L can give us 3 ML values, which are -1, 0, and a +1. And that is a 2p. And a 2p is going to have 3 degenerate orbitals. And these 3 is what we are writing here. Now, when we go to the third energy level, then we have these possibilities here. And these possibilities are actually coming from the value I've lost something. Are you hearing me? I think something has jumped somewhere. Are you hearing me, students?
We can hear you.
Oh, yeah.
I can hear you.
I think something jumped, eh? So let me go back to what I was writing. Yes. So we have this. So that for the value of N is equal to 3, we are going to have 3 possible L values. These are the 3 possible L values. And for each of these L values, we are going to have the corresponding ML values. For example, when it is equal to 0, This is also 0, and you get a 3s. It is only 1. When L is equal to 1, you'll have 3 values of ML, and that is a 3p. There are 3 of them. When L is equal to 2, you will have 5 different values of ML, which are these ones here, and that shell is 3D, and so forth, and so on. Now, this illustration I'm showing in this slide, it is the one that tells us what is the maximum number of electrons that we can find in a particular energy level. Now, if you look at this one, you just look at how many ml values we have. 1 ml value is equivalent to 2 electrons. So for n is equal to 1, you can only have 1 possible ml value, and therefore the maximum electrons that you can have are 2. When you look at n is equal to 2, this is how we are going to get the number of electrons. This one is going to give us 2 electrons. This one is going to give us 2 electrons. This one, 2 electrons. This one, 2 electrons. So the total number of electrons here is going to be 8. 2, 2, 2, 2. When you come to n is equal to 3, you are looking at that level, and you will realize that just like we have said, these are 2 electrons, 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 2 electrons. If you count, you are going to find that they are 18. Okay? So we move on. The energies of those particular electrons are going to be given by this figure here. So it shows the relative energies for the hydrogen atom shells and the subshells. And you will realize in this diagram that a 1s lies very low, a 2s and a 2p follows, a 3s, 3p, 3d follows, 4s, 4f, 4d, 4 follows. Now, this is only true for the hydrogen. And when we go to multi...
Excuse me, sir.
Yes.
Would you go back to the previous image kindly?
Yes, here.
Okay. There is something weird. Probably I have not gotten it very clearly.
Yes.
Okay. L is equals to n minus 1. Now that is okay for the first row. For the second row. Okay, when we start a new orbital, n minus 1 doesn't really apply for L, because you realize that n minus 1, for example, for n is equals to 2, that will be 1. So I would expect L to be 1. So I think maybe you put an emphasis on when you enter a new energy level, L is automatically 0, because you can't take n minus 1. For example, for n is equals to 4, n minus 1 is 3, of which L there is 0. So
okay,
maybe just put an emphasis on that.
The emphasis here is this. When you are given n, then when you have n, then L will be equal to 0 all the way to n minus 1. That is the rule. The values of L will start from 0 all the way to n minus 1. Therefore, when you are talking about n is equal to 2, the values of L will be 0 and 1, because we are moving from 0 all the way to n minus 1. When the value of n is 3, then the values of L will be 0, 1, 2, because this is the maximum value, n minus 1. So you start with 0 all the way to n minus 1. When the n value is 4, then the values of L will be 0, 1, 2, 3. Is it clarified? Or am
Yes,
I
it's
answering your
clarified now.
question?
Yeah.
Okay,
Thank you.
good. Okay, good. So this is I was saying that this particular diagram applies for the hydrogen atom, but when we go to the multi-electron atoms, then this arrangement is going to shift, and we are going to discuss that when we start filling in electrons in atoms. So far, we have been discussing 3 quantum numbers, and remember I said that we have a total of 4 quantum numbers. So here I just want to mention the last quantum number, which is ms. This one is going to show the direction of a particular electron, not the direction of the orbital. It is the direction of the electron or the orientation of the electron in a particular orbital. And there are only 2 possible values of ms. It is either a half or negative a half. Those are the only 2 possible values that an electron can have. Conventionally, we say that when an electron is, for example, written like this, that is positive a half, and when the arrow faces downwards, that is negative a half. That is how we conventionally illustrate the spin quantum number. So the examples that I may give here are, which of the following are permissible sets of quantum numbers? And I want us to look at the 4 of them. When n is equal to 4, L is equal to 4, ML is equal to 0, MS is equal to 0. Is this one allowed? The answer is no, because when n is equal to 4, we cannot have an L value equal to 4. The possible L values will be 0, 1, 2, 3. So this is not permissible simply because this L value is not in agreement with a value of n equal to 4. Now, let us look at B. Is this allowed? When n is equal to 3, we can have an L value equal to 2. We can have an ML value equal to 1. We can have an MS value equal to negative a half. So that is allowed. Now, when n is equal to 2, we can have an L of 0. We can have an ML of 0, but we cannot have this MS. MS can only be positive a half or negative a half. So this one is not allowed. We have also seen that this one is not allowed. Let us look at the last one. When n is equal to 5, L is equal to 3, ML is equal to negative 3. That is possible. And this one is equal to half. So this one is also allowed. So we can say that A is not permitted because when n is equal to 4, the maximum value of L is equal to 3. So we cannot have an L value equal to 4. So that explanation is given here. Okay? Another example is here. State whether each of the following sets of quantum numbers is permissible for an electron in a particular atom, and then you explain why. Okay? Look at this. When n is equal to 1, is it possible for us to have L value equal to 1? No. Therefore, this one is not allowed simply because this L value is not possible. Now, when n is equal to 2, can we have an L value equal to 1? Yes. Can we have an ML value equal to 0? Yes. Can we have an MS value equal to a half? Yes. So this one is allowed. Let us look at number 3. When n is equal to 3, can we have L value equal to 1? Yes. Can we have an ML value equal to negative 2? No. Because this ML value is coming from L value, And the only possible values are -1, 0, and 1. So this is not allowed. When you look at D, everything here is not allowed because we cannot have MS equal to 1. MS can only be positive a half or negative a half. Do you understand those arguments, students?
Yes.
Yes, so that is how you examine, and that one is explained here. So we have talked about an s orbital, a p orbital, and a d orbital, and I just want to show the shapes of those particular orbitals. An s orbital is spherical in shape. A p orbital is going to look like number 8. The d orbitals are going to be having different shapes. And here I am showing an s orbital. It is spherical in shape. So this is a 1s orbital. This is a 2s orbital. You will realize that a 2s orbital is bigger than a 1s orbital because a 2s is in a high energy orbital. A 1s is in a low energy orbital. Remember, we say that as you move further away from the orbitals, the energy increases. So you can see an s orbital is spherical, but you realize that a 1s is smaller, a 2s is larger, a 3s will be even larger. And it is the same thing that is going shown here, the contour view of those particular orbitals. P orbitals, I say that they look like number 8, and this is where I want to show the directionality. Somebody asked me about directionality, and I want to illustrate that in this particular slide here. We have 3 axes, the X, Y, and Z. And you'll realize that this is a PX orbital. It is lying on the X-axis. A PY orbital is lying on the Y-axis, and a PZ orbital is lying on the Z-axis. Remember, for P, we are talking about -1, 0, and 1, because these are the possible ML values. So this is where we are getting the 3 orbitals from, the PX, PY, and the PZ. So this one is actually showing you the directions of each of these particular orbitals. This information is very important because much later you'll be talking about the theories that are used in the formation of bonds, a single bond, a double bond, a sigma bond, a pi bond. This information will be very important in that. Then
Excuse me, sir.
Yes, sorry, I think there are many questions. Yes?
Kadisha, you can go first.
Could you pardon the directionality?
Yes. Now, if you look at this slide that I'm showing here, this is a p orbital lying on a 3-dimensional Cartesian plane. And you'll realize that this one is lying on the x-axis. And we are calling it px orbital. The second one here is lying on the y-axis. And we are calling it y orbital. The third one here is lying on the z-axis. There are 2 lobes. They are lying on the z-axis. We are calling it what? The z orbital. Here we have illustrated using the 2p. The 3p, 4p, 5p, 6p are going to have exactly the same shapes, the same directions if they lie on the particular axis. The only difference is that they are going to be bigger because they lie in orbitals of high energies. The first question is clarified?
Yes.
Kadisha, there was another question.
Yes, okay. I've not quite understood the shapes because if you look at the dumbbell shape of the 2px, you'll
Yes.
notice that one dumbbell lies between the y and x plane, and the z axis is totally untouched. And then for the 2py, you notice that it touches on the z, the y, and the x. And then the 2pz, it touches on the z and y axis, but it doesn't touch on the x orbital, on the x axis at all. So would you clarify on this?
Yes. this illustration is simply showing you a 3D. Maybe I should do this. Say this one, for example, is Y and this is X, okay? A PX will be like this. I may not draw a very good one, but a PX is going to lie here. A PX is going to be like that. It is going to lie on the X-axis. Forget whether it might be touching on the others, but it is squarely lying on the X-axis. If we were to draw a PY will only lie on the Y-axis. That is the simple explanation. The reason as to why here it appears to be touching on the other, because this is a 3D shape. It's a 3D orientation. Is it clarified?
Oh, yeah. Thank you.
Yes, yes. Another question? Okay. So what I want to show is the d orbitals. There are 5 of them. We have dx squared minus y squared. You will see the lobes. The lobes lie on the x squared and the y, the x and the y. Then we have dxz. These ones actually lie on the space. Then we have dz squared. We say that this is a little bit more complicated. Then we have dxy and dyz. This just to show the 5 d orbitals that we have in space. Any question about them?
I have a question.
Yes.
As you're talking about X, Z, and Y, are these just letters used to name the Cartesian plane? Or
Yes,
do they...
yes. These are coordinates of the Cartesian plane.
Okay.
Yes. Any other question?
Okay, is there any scenario in an examination situation where we will be told to sort of identify the orbital drawn? Like, do we have to master these shapes?
It is important that you master them because we can actually ask you to identify.
Okay.
Yes. Another question? Okay. If there are no questions from you, we are only a few minutes to the end of the lesson. You will allow me take the record of attendance, and I'm going to do it from the system. So let me just open that. So when I call out your name, just unmute and answer. Awar? Awar?
Present. Present.
Malena?
Present.
Lindsay?
Present.
Jaro?
Present.
David?
Present.
Aisha?
Present.
Kaunda?
Present.
Gladys?
Present.
Alan Koech?
Present.
Bruce Lihanda? This was the first student to join. Bruce, are you in? Bruce?
Present.
Joy Marango?
Present.
Doris Bugwa?
Present.
Doris, did you submit your practical?
Yes, I did.
On Blackboard? Doris?
Yes, I submitted my practical.
You had sent it to me on email. Did you submit on Blackboard?
Oh, yes.
Okay.
No.
You have to submit it on Blackboard. Remember, I told you before.
Okay, I'll submit it.
Submit it on Blackboard. Ian?
Yeah.
Ian, are you in? Ian? Did anybody see this student in today's lesson? I have no option other than marking absent. Melinda, is it Minda? Ted?
Present.
Maya?
Present.
Kadisha?
Present.
Neema Ngari?
Present.
Fati?
Present.
Olive?
Present.
Lynn Katha?
Present.
Peace Obel?
Present.
How do I pronounce this name now? Olukolamide.
Present.
Can you give me an easier name to pronounce?
Daniel.
Daniel, good. Lucy?
Present.
Oyuga?
Present.
Washira?
Present.
Fabian?
Present.
Wagura?
Present.
Natasha?
Present.
Vivian? Vivian and Vivian? So I'm marking Vivian absent. There's a student I want to find out. Ian Menge. Okay.
So, sorry, sir. Aunt Vivian, she's sick. She was admitted to the hospital yesterday.
Oh, she's not in today.
Yeah.
Okay. So then we have come to the end of the lesson. We'll meet on Monday. If there are questions about what I have taught today, we can handle it that time as we also move on. Is that okay?
Yes, sir.
Thank you very much. You have a good day. I'm going to load a quiz for this week. You have a good day.
Is that a good way to say have a good day?
I think he said what? The camera is on. Someone's mic is on.